Hi, this is Mr. Mack. We're going to talk today about relations and functions. First of all, let's start with relation. A relation is defined to be any set of ordered pairs. Now we have here a set of ordered pairs, the ordered pair 1, 3, 2, 7, 4, 12, and 2, 13. Now if we were to look at this relation in what is called a mapping diagram, we would kind of put an oval to contain the numbers 1, 2, and 4. Sometimes we refer to this as the x's. Sometimes we call this the domain set. That's an important word. You'll need to remember that. And then we would have a second set of the y's, 3, 7, 12, 13. And we sometimes call this the range set. It's kind of important to know that particular word as well. Now, a mapping diagram would be when we show how the elements in the domain are matched with the elements in the range. See, we have 1, 3, we have 2 matched with 7, we have 4 matched with 12, and then we have 2 matched with 13. Now, any set of ordered pairs is a relation. But not all relations are functions. Functions are very important to us mathematicians. A function is a set of ordered pairs, or a relation, where no two distinct ordered pairs have the same first member. Now, if you'll look at our example here, we do have two ordered pairs that have the same first member. 2, 7 and 2, 13 are not the same are not the same ordered pairs, but they both have the same first member. They both have 2. That would make this relation not a function. Now, if you look down at the mapping diagram, you'll notice that there are 2 arrows emanating from the 2. If you have a mapping diagram, if you see something like that, 2 or more arrows emanating from the same element in the domain set, then again, that's not a function. Now, if you were to draw a graph of this relation, we would have the point 1, 3, let's put that about here. We would have 2, 7, that might be here. We'd have 4, 12, that might be here. And we would have 2, 13, that would be here. Now, when you have a relation described by a graph, one of the ways to tell whether that relation is a function or not is to ask yourself, is there any place on this graph where a vertical line would connect 2 points of the graph? And you see, if we get to 2 here, this vertical line at x equals 2 connects the point 2, 7 with the point 2, 13. So we would say that this relation fails the vertical line test, so it is not a function. Now, there are many ways to tell someone what a relation or function is. You can do it as a set of ordered pairs. You can do it as a mapping diagram. You can do it as a graph. You could do it as a statement that tells how the x's or the domain elements relate to the range or the y elements. You could make a chart of x's matched with y's. Any of those are considered acceptable ways to tell what a function is, or what a relation is, or a function is. Now, a lot of times when we're dealing with functions, we like to think of the idea that the domain set or the domain elements are independent. If you had, for example, I can do this, independent, there we go. The x values, again, as we said, are considered the independent variable, and the range values are considered values of the dependent variable. For example, if you were to place a beaker of water over a Bunsen burner and measure the temperature, and then every 2 minutes measure the temperature again as the temperature of water increased, you would probably graph that using time along the x-axis and then temperature along the y-axis, because you would conclude most likely that the temperature of the water depended upon the amount of time it had been over the Bunsen burner. That means that time would be the independent variable and temperature would be the dependent variable. That's an example of independent and dependent. We ordinarily put the independent variable on the horizontal axis, usually that's x, and we ordinarily put the dependent variable on the y-axis, usually that's on the vertical axis, usually that's y. Now, we want to talk about the way we delineate functions with equations. See, if you have a function like y is equal to 2x plus 3, this would be an equation in two variables that would generate ordered pairs. If you picked an x value and put it into the equation, you could solve for the y value that would be matched with it. For example, if you put 2 in for x, you would say, well, 2 times 2 is 4, plus 3 is 7, so 7. That means that this equation would generate the ordered pair 2, 7. You could put 5 in and you would get 13. So we'd also have the ordered pair 5, 13, and so on. Now, mathematicians have decided that the expression 2x plus 3 inherently maps the number you put in, sometimes we call that the input, it's another name for x or the independent variable, and then the number that comes out would be the output, or y. And so instead of using a different variable y to be equal to 2x plus 3, sometimes they'll use a notation that looks something like this, f of x. Now, look at this carefully with me and realize, please, that this does not mean f times x. When you see this kind of notation, or f of x is equal to 2x plus 3, what that means is the function of x is 2x plus 3. So when we give you something like f of 4, what we're saying is put 4 in where x is and figure out what value you get. So f of 4 would be 2 times 4 plus 3. Now 2 times 4 is 8, plus 3 is 11. So we would say f of 4 is 11. Now that would mean the ordered pair 4 comma 11 was an element of that function. But this notation right here, the f of x notation, is just kind of rich with meaning, and it's a very efficient notation, and we'll be using that throughout the year. So you need to get used to that. We do like to name functions with the letters f, g, and h, but we don't exclusively use those. I mean, if we have a function that gives us the area of a circle with respect to the radius, we might call it a of r. A of r turns out to be pi r squared. So this is a function of area with respect to the radius, so a of r is pi r squared, for example. This would be another example of functional notation, and you'll be seeing that a lot.